Welcome to the second part of 3.1b class notes. In the previous video, we ended talking about the logistic regression model that we were able to find to model the population. And this makes a lot of sense. Your population starts with next to no one, right? And then population grows and eventually it's going to taper off and have a nice logistic model. But there's other things that the logistic function can model, and one of those is the spread of rumors. So Julia, who we are going to call for fun classmate number 1, and Ansley, who we're going to call classmate number 2, start a rumor at Grapevine High School. Every minute, someone who knows the rumor tells someone else. So if there are 48 people in the school, determine how long it will take for everyone to know the rumor. So to simulate this, we're going to use the random integer generator in our calculator, but here's the way it works. So at time 0, 2 people know the rumor. So the number of people who know it. So who knows? Right now, person 1 and person 2 know at time 0, right? And so 1 minute later, they're each going to tell someone else. So again, there are 48 people in the school. So what we're going to have our calculator do is randomly pick 2 numbers between 1 and 48. That's what this 2 is. So when we do that, I went ahead and did that. It told me 46 and 44. Those are the 2 random numbers that my calculator chose. So 1 minute later, who knows? Who has heard the rumor? Well, person 1 and person 2, because they created it. And then we said person 44 and person 46, right? That's what my calculator told me, 44 and 46. So how many people total now know the rumor? 4 people. Okay, so 4 people currently know the rumor, and exactly 1 minute later, all 4 of those people are going to tell another person the same rumor. And hence, we're going to randomly generate 4 integers between 1 and 48. So 8, 25, 20, and 36. So these are 4 new people who now know the rumor. So I'm going to jot those down. 8, 25, 20, 36. So 8, 25, 20, and 36. So now we have a grand total of 8 people know the rumor. And so at minute 3, these 8 people are now going to tell 8 new people. Or again, eventually people will start telling other people who've already heard the rumor, right? Because again, say person 1 told person 44 and person 44 told person 8. Person 8 doesn't necessarily know that person 46 knows. So he might tell person 46 or so on and so forth. But let's see what happens when I generate 8 numbers. I've got 3, 17. So I'm going to scroll. Nope, not what I want. I'm going to shrink you down so I can list down here. So we've got 3 is a new person. Oh, this isn't going to work like I thought. 3, 17, 48. So those are all new so far. 3, 17, 48, 10, 39, 46. Bahaha, right there, 46. So 39, but 46 was already told by someone else. So that's our first repeat where someone is telling someone who's already heard the rumor. And then we've got 11 and 18. So, and then 11 and 18. So instead of there being 8 new people, there were only 7 new people who heard the rumor. So 7 plus 8 now gives us 15. All right. So what's going to happen now is these 15 people, right, are now in the next minute going to tell someone else. So what am I going to do on my calculator? I'm going to go to menu, probability, random, integer, and I want to pick a number between 1 and 48. And how many numbers do I want? Well, 15 people are now going to tell someone else the rumor. So it's going to give me this list of 15. And what I'm looking for here is new numbers, new people who've not heard the rumor yet. So 1 has already been told. 45, has 45 been told? Nope, they're new. 6, has 6 been told? Nope, they're new. 1 was already told. 27, that's new. So I've got 45, 6, 27, 42. So 45, 6, 27, 45, 6, I've already forgotten. 45, 6, 27, 42, 47. 47 hasn't been listed yet, so I've got 42 and 47, and 47. And 14 got told by two different people in that minute. 6, 3, 6. I've already gotten 6 and I've already got 3, so 14 is new there. 14. But again, I've already got 6, I've already got 3. 35, has 35 been told yet? Nope, so 35 is new. 1 has already been told. 21 is new. So 35, 21, and then 15 is also new. So again, 35, 21, and 15. 35, 21, and 15. So those are the new people who had not yet heard the rumor. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 new people. So I've got a grand total people now of 24. So after 4 minutes, 24 of the 48 people in the school know the story. So I'm going to go ahead and pause the video, fill in the rest of this, and we'll move on. So pause. Okay, that took a lot longer. I am glad I didn't make you watch me do that. So after 15 people shared the rumor, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 new people for 24. And then I continued and went and went and went and went. And then finally 47 people knew. And I'm like, oh, the next time that last person will be told. But no, it took 7 more times until person 37 finally was told the rumor. Like, this is the person who would say, like, no one ever tells me anything. And he'd be right. But what I want to show you is, if I wanted to answer the question, right, how long will it take until all 48 people know, right? If I use just this much data, 0, 1, 2, 3, 4, 2, 4, 8, 15, 24, on my calculator, I put these into a table, right? And minutes, number of people who knew, right? And you can see there's nothing else below that. Here's what it looks like if I use my menu, analyze, regression, show logistic, right? Pay very close attention to these numbers. So it's 47.678, right? That makes sense. 1 plus 24.29, da, 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 right? It looks like it's going to asymptote graphically at about 47.6, which is what happened in my actual real life situation. It took so much longer until 48th person it finally rounded up. So even this is a good predictor. So like, when will it get there? Well, it gets to the top, according to my graph, at about 10 minutes, right? For me, it took 15. But even with that much data, you're getting a pretty good model. If you were to go back and actually fill in the data, 5, 6, 7, 8, 9, 10, it took 15 minutes before we finally got to 48. We had 47 people know for a good long while. The 7th, after the 7th minute, there were only 42. So 30, 37, 42, 30, 37, 42. Now when we go back, we see the numbers have changed a little bit to adjust to all the extra data that we have, but overall still pretty close to being the same. So what is f of x? 47.6, right? So in this case, it's going to be 47.6 divided by 1 plus 20.2 times e to the negative 0.7x. That's my regression. And where was f of x growing the most rapidly? Well, it's growing the most rapidly between minutes 3 and 6, right? This is so really right around minute 4 is where it's growing the most. This is where it's growing the fastest. So I'm going to say around minute 4, right? Right around here. That's when we have the biggest jumps. From 15 to 24, there's 9 new people. And then from 24 to 30, that's 6 new people. So around minute 4. Okay. So just a few more things from the last little bit of 3.1. Let f of x be e to the x. Determine f of ax plus b. Okay, so first of all, we can do this, right? F of ax plus b is going to be e to the ax plus b. All right, and rewrite it by applying one transformation to y equals c to the x for an appropriate value of c. So how can I rewrite this so I've got some transformation to c to the x? Well, I can use my properties of exponents and say this is, right, e to the ax times e to the b. And then if I think about, well, e to the b, I can bring that out front. This is just some number, right? I can call it k. And e to the ax, that's the same thing as e to the a all to the x. So I could let e to the a be this number c. And so what's one transformation? So I could say, well, this is k times k times c to the x. And so what did I do? I just stretched this function vertically by a factor of k, where k is e to the b. So this is a vertical stretch or a shrink, depending on whether e to the b is bigger than 1 or less than 1, by a factor of k of y equals c to the x, where c is e to the a, this constant. Okay. So in the last couple minutes here, practice using the law of exponents. See what you remember and solve for x, right? 3 to the x equals the square root of 3. How do we solve that? Well, the square root of 3 is 3 to the 1/2. Exponent, exponent, same base. X must equal 1/2. All right, so please go ahead and pause the video right now and do these last 2 problems, B and C. Use the properties and laws of exponents to solve for x. I'm going to pause it. You pause it. All right, so now that you have done these, let's go through them together. So again, 3 to the 3x plus 1 is going to equal, again, I need the same base. 9 is 3 squared, all to the x minus 2. So this is the same thing as 3 to the 2x minus 4. We multiply our exponents, 2x minus 4. So setting my exponents equal, 3x plus 1 is equal to 2x minus 4. If I subtract 2x from both sides, if I subtract 1, that means x must equal -5. All right. And you can always check by plugging this directly in, right? -5, -15 plus 1 is -14. 3 to the -14, is that really the same thing as 9 to the -5 minus 2? Is that really the same thing as 9 to the -7? Yeah, because again, this is 3 squared to the -7th is going to be 3 to the -14th. How about over here? Here, our common base is going to be 5, right? So 25 is 5 squared to the 5x minus 1, put that in parentheses, and this is 5 cubed to the 3x minus 2. So I'm getting 2 times 5x minus 2, so that's 10x minus 2 is this exponent here, needs to equal 9x minus 6. And again, subtract 9x, add 2, and in this case, x is going to be -4. And that's it. And there's the solutions. Whoa, typo. This should be a -5. Minus, right? But there's, again, the solutions in typed out form. And that's it for 3.1. So go after the homework. If you have any questions, email me, come see me, and have a good weekend.